Welcome back to Math 8, Unit 7, Lesson 14. I am quite excited to actually go through this lesson because I am ready to move on with scientific notation. I think you're ready to. Today we're going to start multiplying and dividing with scientific notation to answer questions about animals, careers, and plants or planets. To get us started, we need to know, are these equations true or false? As we look at them, let's look and see and explain some reasoning. When we look at these two values, we can think about these as two independent expressions in scientific notation. But at the same time, we can look at them as just independent values because the operation is just multiplication. If I go 4 times 10 to the fifth times 4 times 10 to the fourth, do I get 4 times 10 to the 20th power? What I should be looking at here is looking at the things that are alike. Perhaps it would be easier if I went 4 times 4 times 10 to the fifth times 10 to the fourth, use some commutative property to group like terms. And I see 4 times 4 is 16, and 10 to the fifth times 10 to the fourth is going to be 10 to the ninth by the product of power rules. And there's no way that this is going to be 4 times 10 to the 20th power. There was a misconception in how to be able to work with these powers. We don't multiply the powers together unless it is a power of a power. So the first one, false. And here's our reasoning. The second one says 7 times 10 to the sixth divided by 2 times 10 to the fourth. We know that these are separate values, and so we can think about them as separate values. We can think about the 7 divided by 2 as one piece of the operation, and then the powers, we can use quotient of powers, and then the question is, did we apply these correctly? 7 divided by 2 is 3 and 5/10. This is a true statement, 7 divided by 2. 6 or 10 to the sixth divided by 10 to the fourth. Quotient of powers tells me that I can subtract. This is definitely a true statement. And our explanation is going to be a little bit different. Divide finite decimals. And powers of 10. And they used quotient of powers, so this one's true. The final one, 8 and 4/10 times 10 to the third times 2. 8 and 4/10 and 2 are a type of like terms because they are both a value that does not have any powers or be multiplied by any type of power. We see this part, this is good. And then we see 10 to the third times 2. That one might raise a little eyebrow, and it's something that you can think about and go, what in the world, how did they get that? And I think what somebody was thinking was, since this says times 2, then we would multiply that by 2. So this part right here, that makes this false. So the two decimal values or the numbers in standard notation are good, but multiplying by that power is not. Okay, let's start using our information. We're going to use this table, talk about biomass, and we're going to answer questions about different creatures on the planet, and we're going to explain our reasoning with it. So we see humans, cows, sheep, chickens, ants, whales, blue whales, Arctic krill, zooplankton, and bacteria. If you don't know what any of these things are, go ahead and pause the video. Go ahead and check them out on Google real quick. But don't take a lot of time. Come right back to the video. I will tell you, blue whales eat Antarctic krill and zooplankton. These are both types of krill. They kind of look like shrimp. They're just really little. And obviously this one, zooplankton, are much, much smaller. They're actually about 4 times or 10 to the fourth power times smaller than these ones. So which creature is least numerous? So we want to look right here at the number, and we want to find out, how can I tell when something is the least numerous? I think the easiest way to do this is to recognize that we have powers of 10 here, and those powers of 10 tell us how many place values will come after the finite decimal, especially the leading digit. Blue whales, we see, have 10 to the third power. There is no other power of 10 that is anywhere close to that value. It's super small. So when we see which creature has the least numerous, blue whales. Estimate how many times more ants there are. When you see this word, these words, this phrase, how many times more, this is an indication you need to divide two values. So as we divide, we're going to take the number of ants. Excuse me, not that number. Let's take this number, 5 times 10 to the 16th power, and divide by the number of blue whales, 4 and 7/10 times 10 to the third power. Now, when we talk about estimating how many more ants there are, one of the things that we can do with this is we can say, 5 divided by 4 and 7/10. Since these are such large numbers, we can go ahead and use our estimation to say, that's pretty close to 5. 5 divided by 5 is 1. Times 10 to the 16th, the quotient of power says subtract the exponents, times 10 to the 13th power. That would mean that we're saying there are about 1 times 10 to the 13th power times more ants. Just in case if you weren't sure about 10 to the 13th power, that's 10 trillion. Think 100,000 million, billion, trillion. Yeah, 10 trillion times as many ants on the earth. So which creature is the least massive, the smallest one? Again, go to the powers of 10 and look for the smallest power of 10. In here, we can see that bacteria is the smallest power of 10, 10 to the negative 12th power. So the least massive would be bacteria. And estimate how many times more massive a human is than the bacteria. So we go up to the humans, 6 and 2/10 times 10 to the first power, divided by bacteria, 1 times 10 to the negative 12th power. And this one's kind of cool because I know anything divided by 1 is itself. So this would be 6 and 2/10 times 10 to the first power divided by 10 to the negative 12th power would be quotient of powers again. That would give us 1 minus negative 12. So we have 10 to the 13th power. And then we can say humans are about 6 and 2/10 times 10 to the 13th power. That would be 62 trillion times more massive than bacteria. Pretty amazing how much bigger we are than bacteria, or pretty amazing how small bacteria really is. So which is more massive, the total mass of all the humans or the total mass of all the ants? How many times more massive is it? This one means that we have to do a little bit of work. If we're looking at all the humans on the earth and all the masses of all the mass of all humans, then we have to do some calculation right here to figure out what the total mass is. In this case, the total mass of all humans and the total mass of all ants, we have to do a little bit of multiplication before we can do the division here. With the humans, we can take the total number of humans, 7 and 5/10 times 10 to the 9th power, and multiply that by 6 and 2/10 times 10 to the first power. We'll get another number out of this one. We'll go ahead and use a calculator at this time. And we'll figure out 7 and 5/10 times 6 and 2/10. We want to collect the finite decimals first, find their product. And then mentally, I think we're pretty easy or pretty good at product of powers here, times 10 to the 10th power. Now, this is not scientific notation, but no worries yet. We'll fix that part at the very end. So there's humans. Let's talk about the ants now. We have 5 times 10 to the 16th. Times 3 times 10 to the negative 6th power. This one's kind of nice because I know 5 times 3, there's 15 times 10 That's 16 plus negative 6 would be 10 to the 10th power. Now, a neat thing that we see right here is we have both these powers of 10 are the exact same. My last step will be to divide the number of humans, or excuse me, the total mass of all humans divided by the total mass of all ants. The total mass of all humans was 46 and 5/10 times 10 to the 10th power, and then 15 times 10 to the 10th power. You might be asking, well, why is this a good thing? Well, 10 to the 10th power divided by 10 to the 10th power is 1. That part's pretty simple. We go back here to our calculator, 46 and 5/10 divided by 15, we get 3 and 1/10. And we find out that the mass of all humans is about 3 and 1/10 times more massive than all ants. Now, I think that's pretty impressive because when you think about an ant, you might be wondering what kind of ant. Let's just pay attention to this part of about an ant, that we as all humans, there's enough ants on the earth to come that close to our total mass. Is pretty amazing. So which is more massive, the total mass of all the krill or the total mass of all the blue whales? We would do the exact same thing here that we just did with the previous problem. All the blue whales, 4 and 7/10 times 10 to the third, and then multiply that by their total mass, 1 and 9/10 times 10 to the 5th power. And just in case, if you really want to know how big a whale is, that's 190,000 pounds. 190,000 kilograms. Sorry. Multiply that by 2 and 2/10, and you're looking at the weight of a blue whale. Is about 418,000 pounds. That's pretty amazing. When you think about tons of weight, that's over 200 tons of weight. And that helps you understand why the population of the blue whale is so small, because they are such a large animal. Anyway, interesting thought, in my opinion. We would divide this one by the total number, or the total mass of all the krill. So Antarctic krill, 7 and 8/10 times 10 to the 14th power divided by 4 and 86/100 times 10 to the negative 4th power. And once I have those values out here, I would do the same thing, take the division, and then interpret my answer. Only this one's going to be slightly different in the way that we go and we finish our interpretation. 4 and 7/10 times 1 and 9/10 gives us 8 and 93/100 times 10 to the 8th power. And then we'll look at the next one. And we have 7 and 8/10 times 4 and 86/100 is 37. That doesn't feel right. Just a second. Wondering if I typed anything in wrong. Okay. Times 10 to the 10th. Now, there's a problem here. This says which is more massive. And I didn't account for that in the beginning. And what I see with this is that the amount of krill is actually more massive. So krill are, and now this is the total population. The mass of all the krill is greater. And then how many times greater, I'm going to have to take this and flip it over to do 37 and 908 thousandths times 10 to the 8th power divided by 8 and 93/100 times 10 to the 8th, or 10 to the, whoa, I messed up. 10 to the 10th power up here, 10 to the 8th power here. The 10 to the 10th divided by 10 to the 8th is pretty simple to calculate. And then I do this next part, divide 8 and 93/100. And I can go ahead and round this, but when I round it, I want to say approximate, squiggly equal signs. Approximately 4 and 25/100 times 10 to the 2nd power. When we interpret this, it says about how many times more massive in it. We can say about, we want to simplify this, 425 hundredths times 10 to the second power is 425, about 425 times greater mass. So when you put all the krill together, as heavy as a whale is, right, that 380, no, what was it? It was like 400 something tons, right? 400 some thousand, right? 418,000 pounds per animal, right? And they estimate that there's somewhere around 47,000 or 4,700 of them. That's a lot of weight, but then you put all the krill together and it's way bigger. Okay. Looking at the next one. We're looking at the distances in the solar system. We'll go a little faster in this one. And he goes like this. When we talk about these distances here, we're talking about the distance to Earth, the diameter, and the mass. We're going to use this table, talk about the sun and the planets of the solar system. Pluto's out because it's a dwarf planet. And then we're going to answer these questions. So estimate how many Earths side by side would have to have the same width as the sun. If we're talking about the width of the sun, then this one will be one that we would say we're breaking up the sun into distances of the Earth. So what we'd have to do is take that diameter of the sun and divide it by the diameter of the Earth. So the diameter of the sun, 1 in 392 thousandths times 10 to the 6th power, divided by the diameter of the Earth, 1 in 28 hundredths times 10 to the 4th power. Go ahead and take a moment to calculate that value. Okay. Now, the next piece of this, when you have that, let me bring my calculator back up. 1 and 392 thousandths divided by 1 and 28 hundredths gives us 1 and 0.875 times 10 to the quotient of power, subtract the exponents. And now we say estimate how many Earths side by side it would take. Well, then I take this number and we multiply it by 10 to the 2nd power. We'd have to have somewhere around about 108. So this one, I would probably round up to 109 because we're talking about this is 108 and 75 hundredths. So we can say about 109. How many Earths would it take to equal the mass of the moon? We do the exact same thing we just did a minute ago. We take the mass of the moon or the mass of the sun and divide by the mass of the Earth. Now, just in case you're wondering, smaller number on top, lower number on bottom, we are going to have to change our information here just a little bit. Divided by 5 and 98 hundredths. And what I mean by a little bit is because of this. This is not going to be scientific notation. So when we answer this question, we have to think in a little bit better terms with this. 10 to the 6th power. When we go to answer how many Earths would it take to equal the mass of the sun, we need to be able to multiply this by 1 power of 10, which will reduce this one by 1 power. To make this one bigger, I have to multiply by 10. I have to borrow it from here, just like I would do a subtraction. Like if I had something like 71 minus 99, I would have to borrow from my tens to be able to make the next place value bigger so that I could actually make that subtraction happen. This wasn't a really good example. It's still going to show us a negative number, but you get the idea. Here, just to make it work, we'll call this one 59. And then that way we can get 12. Okay, so that means that we have a number that is 3 3/10 times 10 to the 5th power. we would interpret that 3 times 3 and 3/10 times 10 is 33 times 10 times 10 times 10 times 10. And we would say that we have about 330,000 Earths to equal the mass of the sun. Estimate how many times farther away from Earth the planet Neptune is compared to Venus. If we're talking about the difference is how many times as far away. This is another one that's a division piece. How many times far away from Earth to Neptune, or excuse me, from Earth, the planet Neptune is compared to Venus. We're going to have to take a little bit of those pieces with the distance to the Earth. We would look at Neptune and Venus and which one is further away. Neptune, 4 and 3/10 times 10 to the 9th power, divided by Venus, 4 times 10 to the 7th. Beautiful part again. Estimate 4 and 3/10 divided by 4. I can say that 3/10, that's about 30 divided by 4. It's going to be about 7. So I would see this as approximately 2 and 7/10 times 10 to the 9th divided by 10 to the 7th, 10 squared. I'd say around 270 times. Let's see how close I am. 1. Oh, whoops. I was way off. Let's fix this. See, I was way off. That makes a big difference. This comes out to a value of about 107 and 5/10. And so I'd say that Neptune is approximately 107 5/10 times further away from the Earth than Venus. Okay. And that kind of helps us understand why it's so hard to get out to these other planets in our solar system. The last one is about professions. Actually, excuse me, there's one more question. Estimate how many Mercuries it would take to equal the mass of Neptune. When we're talking about Neptune and Mercury, that means we're going to take Neptune divided by Mercury. So that'd be the mass divided by the mass. That one I want you to do on your own. Give it another shot. And then I'll just play with the professions here. This is, again, the same following information. These are all different professions with the different number of those value of those jobs and their estimated annual salary or a typical annual salary that goes with it. You would answer your questions about the professions and express each answer in scientific notation. Talking about how many times more nurses there are than doctors. Again, how many times more division. How much money do all doctors make? This one would be a multiplication. And how much money do all police officers make? Another, again, it's a multiply. And then who makes more money? All enlisted military put together or all military officers put together. That would be some multiply, followed by estimate how many times more division. Knowing what these operations are can help us to get going with the next steps. If you feel like you're done with the video and you're ready to roll with your work, please feel free. Otherwise, I'm going to continue the video and work out each of these problems. Here is the summary though. Multiplying in scientific notation extends what we do when we multiply regular decimal numbers. For example, one way to find 80 times 60 is to view 80 as 8 tens and 60 as 6 tens, and the product of these would be 48 hundredths. We use scientific notation to go like this. 8 times 10 and 6 times 10 would give us 48 times 10 to the second power. When we go to scientific notation, we would have to bump that power in one place value, making it a little smaller, which would add 1 power of 10 to my powers of 10. This is especially useful when we're talking about very large numbers. So please watch for those pieces and understand that calculating in scientific notation is much easier in multiplying and dividing than you really think. So give it a shot, follow directions, and stick around if you want to see how to do these next parts. If not, have yourself a great day.